So one of the many properties of a substance which is affected by the intermolecular forces, or IMF, in that substance is the viscosity of a particular liquid. So we have a little demonstration that might help you think about intermolecular forces and how they affect this property. So first things first, let's define viscosity. Sometimes you'll hear people call it an internal friction. It's a measure of how molecules can move or flow relative to each other. As we talked about in class, how liquids, molecules can move and flow. And a molecule that can move and flow around each other very easily has a low viscosity, where a molecule that's tangled or has a lot of forces keeping it from moving has a very high viscosity. So viscosity is dependent on the intermolecular forces inside the molecule. Liquids with a higher intermolecular force have a greater viscosity. If you want to think of a classic example of a liquid with a very high viscosity, think of something like pancake syrup or honey, something that's very slow to pour from the container. Those are molecules with a very high intermolecular force, which I can tell from their high viscosity. Another thing is that you do have to watch out for temperature. Viscosity is inversely proportional to temperature, because if you think about what's happening as the temperature increases, the molecules have a greater kinetic energy. So that greater kinetic energy helps to overcome the intermolecular forces between those molecules and allows them to move. This is why if you've ever looked at a container of motor oil, you'll notice they have two numbers on them. It'll say something like 5W20, and that is actually looking at a hot viscosity and a cold viscosity, and you pick the right one for your engine and what it needs. So we're going to look at three molecules in our demo, and here's the first one. It's often called propylene glycol, but the proper name for it is 1,2-propane diol. It has 3 carbons in a row, which is why we have the prop, and it has 2 alcohol groups, so the diol, the 1,2, tells us that they are next to each other and not on the opposite ends. If I wanted to expand out this organic line structure, of course, every carbon needs 4 bonds. So any place I don't have an OH, I would fill in with a hydrogen to have a complete number of 4 bonds. So now your task is to think about what intermolecular forces would be found between the molecules of 1,2-propylene glycol. And you can just basically make a quick little list. So I'll give you a couple of seconds to think about this and predict what you would see. Well, of course, every molecule everywhere has a London dispersion force because it has an electron cloud, so it has a polarizable electron cloud and can have an induced dipole-dipole force. But the other thing I see here is the OH, the alcohol group. And anytime, remember that I have a hydrogen directly connected to oxygen, I have the possibility of the hydrogen bonding force. And in this case, I have 2 possible places where I can form a hydrogen bond between these molecules. So that's something to think about when I want to compare intermolecular forces. How many different times can I form a hydrogen bonding force between the molecules? In this case, I can do it twice. So the next molecule we're going to look at is very similar. It is glycerin. And it is, in fact, 1,2,3 propane triol. So again, 3 carbons. But now instead of having just 2 alcohol groups on the 1 and 2 carbons, I have 1 on each carbon. So again, I'm going to give you a couple of seconds to think about and make a list of the intermolecular forces that would be found between these molecules. And if you got basically the same list as between 1,2 propane diol, you are correct. Of course, there would be a London dispersion force since this has an electron cloud that can be polarized. But now I have the option of hydrogen bonding 3 times across this molecule. The last molecule that we'll look at is a little harder to classify simply because there's a lot of different things that can go into this mixture, and it is mineral oil. Mineral oil is made of a bunch of various hydrocarbons, and this is only 2 of the possible examples that you could find, and different grades and varieties of mineral oils will have different components. But they are made out of paraffins, isoparaffins, and other cyclic carbon-hydrogen compounds. So just blowing up the carbon-hydrogen chain, here is an example of a paraffin that would go on for a while, and a branched paraffin where I have carbon substituents at various points along the chain. So this is a very long molecule made out of lots of C's and H's. So again, I'll give you a couple of seconds to think about the intermolecular forces that would be found between these molecules. In this case, we have a pretty short list. Since this is all carbon and hydrogen, this must be a nonpolar molecule. There are no polar bonds, and so it cannot be a polar molecule. That means the only possible force I could have here is the induced dipoles of the London dispersion force. There cannot be any dipole-dipole or hydrogen bonding interactions between these molecules. So now that we've listed the intermolecular forces involved, let's think about how they're going to predict and how they're going to affect the viscosity. Instead of studying how the liquid flows itself, which would be a mess and require me to pour liquids and see how long it takes for them to travel, we're going to study it a little bit indirectly. We're going to study how an object, a steel ball bearing, moves through the liquid, because the molecules have to be able to move to allow the ball bearing to fall through it. So we have to think about what will happen to the time it takes for the object to travel in a viscous liquid. Well, and of course, if you think about it, if you have a molecule that's difficult to move, it's going to take more time for that ball bearing to be able to fall through it, because it's going to take more energy and time to move the molecules out of the way of the object as it falls. So the more viscous the liquid will be, the longer the time it will take for the ball bearing to travel through this liquid. We have these tubes that have markings so that we can actually compare the distance, and we'll know that they do travel the same distance so that we can just compare the time. So your job right now is to make a prediction, to rank the molecules from the one you think you will find the least viscous to the most viscous. Of course, how are you going to do that? Well, you're going to predict the strength of the intermolecular force and think about how a stronger intermolecular force affects the viscosity. So I'll give you a little bit of time to make a prediction, and then we'll go on and we'll do the experiment. We'll try several trials and then average the times together. So I have several tubes, of course, that have the same diameter, and I've marked off the starting and ending mark that was engraved in the tube by the company, so that, of course, we can compare the time it takes to travel a certain distance through a fluid. Now I have propane diol, and as you can see, I have again marked the starting and ending point with some yellow tape so that we can see it very clearly. And we're going to drop the ball bearing in the top, travel on down through, and we'll time it to see what happens. So, okay, drop it in. Oh, well, that was very fast. So let's try again. Start, stop. So it just took a couple of seconds there. So we'll try another trial to make sure our results are consistent. Start, stop. Start, stop. So through the propane diol, it is a very quick transition. And this fluid is glycerin. And so I'm going to take a ball bearing and I'm going to drop it into this solution, and we're going to time it. And stop. So we'll try putting the ball bearing into the glycerin tube now. And we'll time it from when it crosses the yellow stripe at the top down to when it hits the yellow stripe at the bottom. So start. Stop. And let's do another trial to see if our results are consistent. Again, we're going to start when it crosses the top yellow mark and stop timing when it crosses the bottom yellow mark. So I'll drop the ball bearing in, start. Stop. Mineral oil is hydrocarbons, just C's and H's. So we have a different profile of possible intermolecular forces here. Let's see how long it takes to traverse the space between our two tapes if I am using mineral oil. Start, stop. Okay, so try this again. Start, stop. And start, stop. So you can see there are some similarities here in the amount of time that it needs to travel, even though the intermolecular forces causing the interactions between the molecules are different. So we'll do one more. Start, stop. I went back and I watched the video clips with a stopwatch and timed the runs, made an average of the time for the 3 runs for each of the substances. And so we can see that through the propylene glycol, the average time of travel was even less than a second. It was almost as fast as it hit the start, it hit the stop. It was only 0.68 of a second. Where when we got to the glycerin, It took considerably longer to go through the glycerin at 12.4 seconds on the average for all three trials. And mineral oil was in between the two. It took 2.20 seconds to travel, so not anywhere near as long as the glycerin, but certainly a considerable amount longer than the propane diol. So now that we have these times, let's think about what this actually means. So I think some people are probably surprised by these results. I would be pretty surprised if many people had picked mineral oil as being actually more viscous than the propane diol, because there's a really common misconception that molecules with only London dispersion forces must only have very weak intermolecular forces. This kind of information is a very common way for AP to approach intermolecular forces. You'll often be given information like this and be asked to use the intermolecular forces to make sense of the data. For example, they could give you a table of viscosities and ask you to explain why the viscosity of mineral oil is greater than 1,2-propane diol when comparing the intermolecular forces between the two. It's a kind of common question simply because, as I said, many students have a misconception that London dispersion forces are always a weak force. But if you look back at the structure of mineral oil, it is a huge molecule with a very large, very polarizable electron cloud. And if you have a large polarizable electron cloud, the induced dipole of a London dispersion force can actually be very strong. Just think about something as simple as wax, candle wax. We know that candle wax must have a higher melting point than water because water is a liquid at room temperature and candle wax is a solid. So even though water has hydrogen bonding forces, the enormous polarizable electron cloud in wax actually means that the London dispersion force results in a stronger intermolecular attraction because of its large polarizable electron cloud, giving us a huge induced dipole. So it's not always as simple as just saying, oh, hydrogen bonding equals strong force. You have to think about things like size of the electron cloud and how that will affect the London dispersion force, even if a molecule is non-polar.